There are many challenges with fossil fuels, and much of this is because the process of extracting these resources is inefficient and dirty, and our ever-increasing demand for energy creates challenging political situations. Hey everybody, this is Chris Brandt here with another FUTR podcast. Upwing Energy is bringing new technology to make the extraction of fossil fuels more effective. Sometimes the path to a greener future is incremental through key improvements to our existing systems, making them cleaner and more efficient. And that's what Upwing's doing. Upwing's solution lets us extract more from our existing resources, making us less dependent on dirtier options or foreign resources. So let's talk with Herman Artinian, CEO of Upwing Energy, about what they are doing and how it all works. Welcome, Herman.
Thank you.
Well, thanks for being on. This is going to be an interesting conversation because, we were talking before and I mentioned how I like the nitty gritty of how key infrastructure things work. Why first is drilling wells so inefficient, and why is so much of those resources left in the ground so that we have to continually, go into new areas and start drilling?
Great question. But just to make sure, drilling unconventional shale assets is not very efficient. And that's
Right.
where we are right now. So today, in the United States specifically, 85% of our natural gas production comes from unconventional shale assets that have to be drilled, fracked, as then the recoverability of those, what's been determined to be underground, we only are able to recover 10 to 12% of that.
To think that only 10 to 12% of that is actually being extracted?
Yes.
It's
a name
wild.
of economics, right? I mean, you
Yeah.
could justify it with X amount of production, with X amount of cost. The market is happy to pay, and there you are. Versus you roll back, 20, 30, 40 years ago, large, what we call conventional. Basically, you just had to drill one, for analogy purposes, put your straw in, and it's been producing for decades and decades and decades. So
Put your straw in. I like that.
That's it. That's what we do.
For example, in Los Angeles, there's all these little buildings all over Los Angeles with beautiful facades, but they're really just fake facades and with oil rigs, for example. So, these things are all over the place too.
It's all over the place, and it's necessary. And I didn't even know about those facades, in West LA for years and years that I lived here. Only recently I figured out when I saw these fracking trucks and stuff enter from the back. It's like, where are they going? In this beautiful condo. It's not a beautiful condo.
But those are some of the old traditional resources, right? I mean, those things have been around for a long time.
That's right. I mean, I live in Huntington Beach. And if you look at some of the pictures of Huntington Beach, Long Beach, from the 30s, 40s, you will not be able to recognize it was Huntington Beach. Every 10 feet, there's oil there. There's an oil well. It's amazing.
That's crazy.
Yeah, and we still have some all over the place. A lot of offshore as well.
So they're only getting 10 to 12% of the resources out of that.
Unconventionals, yeah. So when you're talking about the fracking industry that revolutionized these unconventional assets in Pennsylvania, some parts of Haynesville in Texas, it's all about how cheap you could drill and how fast you could bring it to production. That's the cycle. And I don't think it's environmentally sustainable at the rate that they're going. Just for natural gas, we need to drill somewhere around 4,000 to 5,000 wells per year to be able to meet up with demand. Forget about the demand that's growing, just to meet today's demand.
Those wells are often not drilled in places where we want them to be. They impact natural, landscapes and natural habitats of wildlife and things like that, right?
Sure. I mean, look, I have to give some credit. It's not as bad as it used to be 15 years ago. We've gotten smarter. Data has made us, simply economics has driven the necessity for us to get better, safer, and so on and so forth. But if you look at the flip side, all these assets that have been producing for 20, 30, 40 years, they still have good 40, 50, 60% of the hydrocarbons sitting down there when we're talking about natural gas. So we could bring those up.
The more we bring up out of the existing wells, the less we have to impact the environment with other wells. So, like, why is it so hard to get all that out? I mean, like, you say stick the straw in there and try to pull it up, but what's causing the limitation there?
We've solved a lot of the pieces of the puzzle simply because economics created the necessity and the means for us to be able to do that on the oil side. So we have a lot of what we call enhanced recovery for oil. We inject CO2, we push with water, and we push the oil out. There is CO2 injection. We pump natural gas to change the viscosity to bring it up. So as the economics permit, we come up with widgets and technologies and processes to bring them up. But nothing has been done on the natural gas side up to now. Up to now, we leave it for the mother nature. There's a build-up pressure when we drill. That pressure kind of brings it up. And we leave the rest because it's not attainable. Fracking has brought this unique capability to be able to go into what we call very tight shell formations. I mean, you're cracking marble, really, trying to get a little bit of the molecules within the marble, but it comes at a price of 10, 12% recoverability. But today, if you remove the environmental impact out, economically, at $3, $4 gas, it's justifiable.
The way that gas comes up is that it's pressurized. And when you tap that well, there's a natural pressure in there that kind of pushes that natural gas up the pipe, right?
Absolutely.
And so can you talk a little bit about why you can't just, put a big suction pump on it and pull the rest of it up?
There is a big difference between when we talk about liquids and gases. But one thing that's common is it always takes 6 to 8 times more energy to suck versus to push.
Right.
So we figured that out with oil, and we were able to put pumps there. There's like maybe 7 different types of pumps that we developed that we could go down mile, 2 miles down and start pumping the liquids up. But with gas, it becomes extremely more challenging to be able to do so because gas is compressible. I could take a volume of gas and shrink it into this volume just by pressure. But with liquid, just like your hydraulic brakes, it doesn't change volume by pressure. Very, very little.
Well, unless you're dealing with water and trying to, as you say, suck it up a straw at a certain point, because you have to create such a low pressure area within that straw, the pressure drops so much that the liquids start to boil within that, and you can't, suck things up.
And now you're getting into the very heart of the matter, the details of the gas, right? There's a lot of condensation that takes place because these are not pure methane. These have a lot of what we call heavies, like hexane, pentanes, butanes. And as you're bringing them up and you drop the pressure and the temperature drops, all these condensate and they fall right back into the well, creating a lot more friction for the gas to flow up. So the dynamics get quite complex when we're talking about multi-phase flow. In oil, none of that exists. It's just liquid. You're just bringing it up.
The reality of what suction is sort of counterintuitive to how we think about how it all works, right? I mean, really what we're doing is overcoming the existing atmospheric pressure on the thing that we're trying to suck up by reducing the amount of air pressure in that tube. So it's kind of it's not as simple and straightforward as our brains tend to think of it as.
One of the key points that enables us to do what we're able to do. My first physics class, I was floored when my physics instructor, this is Physics 101 with the auditorium of 500 people, when he said he was pushing on this wall, actually the wall was pushing back. And I'm thinking, what do you mean wall is pushing back, right? It's a cement wall you're trying to push. What's wrong with you? But it's the same exact thing. No matter if you break it down at the end, you're trying to create this vacuum on top. And there's only so much you could do, and you're not really putting the energy into the gas. When you put the energy into the gas, which is what you're pushing it now, and that is 6 to 8 times more efficient and significantly much more effective.
You're also talking about a mile, 2 miles down, which is really deep. You're putting pumping systems into that well to create the pressure from down below. So now you're pushing it instead of trying to suck it up.
Exactly. So not only are we using about 1/5 or 1/6 the energy, but with the same amount of energy and less, we're able to bring up 200, 300% more of the natural gas.
When you're pumping it, are you pushing more air into the system to pull it up, or are you just purely pumping from down below to push it up?
The fundamentals of the compressor for those who everyone has used compressor, right? Even when you're pumping your tire, it's some way of a compressor. So at the suction, you're sucking it as you're sucking, you're really dropping the pressure at the area because you're taking some volume away. And it goes through multiple stages of the machine doing work, compressing the gas, increasing the pressure. And at the exit, you release it, and now it's built up pressure, maybe 2, 3, 4 times than the suction. And that just shoots it up with a unique velocity. It wants to get to high pressure, wants to get to a lower pressure as fast as it can.
By taking stuff out, you're creating a lower pressure system down there. So you have to probably replace that pressure, right, in the system. So even as you're pumping it up, you probably still have to kind of backfill that?
No, you don't. So because of this 2-mile journey, there is a significant pressure drop. So we're not releasing it to the ambient. So it's going into a pipeline, and that pipe does already have some pressure. So what we're trying to do is create a drawdown or a suction as close as we could get at the reservoir level, so we could capture as much of the gas as possible that wasn't able to come up before, artificially boost that pressure and release it so it overcomes the friction of the pipe and the pressure on the gathering side on the surface side. We're putting unique energy right where it wants to be to augment the already existing, the Mother Nature's reservoir energy. So it's very little energy what we're inputting into the system.
It sounds very simple, like, well, you're just tossing a pump down a hole. How hard could that be? But I got to imagine it's actually an extremely complex thing, because even running a power line a mile, I mean, you have high voltage long haul cables to do that here, because you put the voltage through at like a wall voltage through that long of a cable. There's a lot of capacitance and resistance. It's probably not going to make it all the way down that hole. So I got to imagine there's a lot of interesting things you have to engineer into that pump to make it all work, right?
The devil is in the details, and we could go on every challenge that we've been through, but I could summarize it by 9 years and $80 million in R&D to get this thing to be commercially ready.
How does that work? How do you get the electricity down there? How do you have a pump that's going to be efficient enough? But I mean, how big is the diameter of that drill hole? I mean, it's not that big, right?
It's not that big at all. But what we do have is a lot of length to play with, 2 miles worth. But the diameter is only 5 inches. That's as big as the tool could be.
Only 5 inches.
The industry wants it smaller now. They want it at 4 inches, so they could put it through even tighter clearances. But so we basically were able to, over this course of 9 years, take, if you have ever been around these shop compressors, these giant things that provide your air shop, even at your tire shop, gas station, we shrunk it into a 5-inch diameter and 12-foot length. And that's what we did. And the power does come with a conventional, downhole conventional cable. So good thing is certain of those technologies have been developed for oil pumps. But the biggest difference with us is never been such a compressor shrunk down to such size, and never has anything downhole been operating at speeds of 50,000 RPM.
Wow.
So because we don't have that big diameter, when we shrink it, we do need to spin it faster to be able to compress at each stage the gas to get it at the level pressure that we needed before we let it go.
And I got to imagine this is not 110 volt, like water pump like I got to, when my backyard floods.
This is high voltage. So we're talking about, I think, 2,700 volts at the machine. And we pump much higher from the top side, so there's some voltage drops along the way, a 2-mile journey, just like your grids, right? There's some losses along the way.
We've kind of hinted around the edges of how this benefits the environment to do this. I mean, I think some people will look at like, oh, well, you're extracting more fossil fuels, but natural gas is used in much more clean uses. So the ability to extract that natural gas is going to lead towards less carbon in the atmosphere in general, right? and by being more efficient with these, we're getting more out of each one, so it's not as problematic.
Before I tell you exactly how we're able to maintain environmental sustainability via our method, I just want to clear out, because even I didn't know about the natural gas usage. I thought I correlated natural gas, electric power. But now that I've been in this business for some time, only 35 or so % of natural gas is used to make electrons. The other uses where today we can't live without is fertilizer, all our food production, all the plastics. And when I'm talking about plastics, yeah, everybody's mind goes to, the bags at grocery store. But your
Right.
cell phones, your chips, your computers, your solar panels. I mean, this is all ethylene-based products. And then the
Right.
other is your residential, commercial, furnaces for ceramic firing, all those things. So car parts, right? I mean, your dashboards, your steering wheel. So
Dyes too.
yeah, absolutely. Absolutely. So I didn't have an appreciation for it, going back 10 years ago, as I do now. So having that cleared out, to come back to your question, there are two things that we're doing that's substantially valuable in cutting down emissions. Number one, currently today, there are a lot of what we call topside compressors. These are natural engine, internal combustion engine driven compressors that are trying to suck some of the gas or push some of the gas in the pipelines. And they are not maintained appropriately. And when I mean that, once a month, somebody's changing seals on this thing. They leak methane. You're looking at somewhere around, on average, I think EPA did the study, 200 to 300 tons of CO2 equivalent per month between burning the gas and then leaks from the seals.
Well, and you're pumping methane too. Methane is a really problematic greenhouse gas, right?
Somewhere around 31 times the CO2 equivalent, right? So it is quite impactful. That's the first one. The second one is, as we can reduce the amount of unconventional drilling and fracking, and what we've done is in the study, we discovered that one of our unit installed in a conventional basin in the Gulf Coast, let's say within the United States, within 8 to 10 years of its life, it produces equal to, if not more, than a well that's drilled and fracked in a Marcellus shale. So if I could prevent one from being drilled and fracked, that's roughly about over 8 million tons. One time CO2 emissions of 8 million tons, plus $10 million in cost of drilling, fracking, and bringing it online, and the infrastructure, plus 5 million, minimum 5 million gallons of water that's required to frack it.
Wow.
That's a significant shift.
Those are big numbers. Those are really big numbers.
Small. Absolutely.
Yeah.
Absolutely.
Yeah, that's going to have a significant impact. How many wells are you operating in now?
We're in about 2-3 right now on trial basis. We're still fine-tune. We have been this year. Our job was to fine-tune the whole process, not just the development of the tool. Development of the tool, we're way ahead of, but we are creating a new market vertical, a new application. This application didn't exist before. So there's some unique, pinpoints in the process of the application, which we're fine-tuning, so that the process is applicable to all wells, and we don't have to pour in engineering for each well. And after we're doing that, we're correlating our models and trying in different wells within Texas, Oklahoma, and Louisiana, in our backyard, if you will. So that will be all wrapped up and done this year. We got a couple more months to go, 3 more trials planned with different operators. And after that, it's all about how fast we could commercialize.
Using your pumps, does that eliminate the need completely for all those topside compressors?
Not all of it, but definitely majority of it. So depending on where the well is and where the processing plant is, if the journey is long enough, you would need boosters along the way. But the ones that are within a mile radius of it, we could definitely eliminate those easily. And there's a lot more of those than boosters, because what happens is pipelines merge and it becomes a single line. So you just need one compressor versus for each well having to need a compressor.
It's funny how much fossil fuel you need to burn to, extract fossil fuel. fuel.
That's right.
And then the leakage there, I got to imagine like eliminating all those compressors is going to be a big improvement.
The operating costs are going up. EPA is cracking down on these leakages, methane leaks at the well sites. So you've seen all these maps of methane leaks and stuff from the satellites. Well, those are real, right? So some operators are much better than others, but there's also a cost associated with those type of an operation. At $2.50, some corners have to be cut. Really, that's a bottom line.
The other side of this too is you look at, like, for example, what's happening in Europe, and considering what's been going on in Ukraine, there's been a lot of challenges around getting enough heating fuel for Europe because of restrictions and access to those natural gas resources, right? So I got to imagine, like, one of the things that I think is really interesting about this is by making more efficient use out of the resources that we already have. I see that as eliminating the need to import and be so dependent on external sources of natural gas. And that can, I mean, energy seems to drive conflict in the world. So, like, having, easier sources to get them from, I got to imagine, is going to have an impact on that as well, right?
Absolutely. I mean, this thing has been brewing for some time. It's just that, unfortunately, this crisis with Russia and Ukraine have brought it to the surface and really made everyone have to deal with it. The natural gas, as the industries and as well as the nations have been thinking, they already had mapped out that we need a lot more natural gas. By the way, it's the cleanest out of all fossil fuels, and there's so much uses for it. Just from, forget about energy, just population growth. And developing nations want their widgets, their homes, their plastics, their cars, their phones. We need a lot more of it to be able to, as a raw material, to bring these up. Now, in US, we're quite fortunate. We have a lot of these natural resources, but other countries don't. So it becomes truly environmental crisis, or more importantly, the energy crisis within the nations, that they need to secure this energy. And we could all agree we need energy, but we end up really disagreeing how we got to get this energy really fast, right? So
well, fusion's right around the corner, right? We're going to all have fusion generators in our basements
next week. Love it. I mean, the closest is nuclear, and they're looking at 2 decades before it becomes viable and available. It takes
and the challenge around nuclear isn't really even the technology of it necessarily, so much as it is the political side of it and the regulatory side of it, just trying to get people comfortable with, like, hey, there's going to be a nuclear reactor in your backyard.
But at the end of the day, it's a strange loop, right? I mean, I need votes, and I need votes from my constituents, and they're saying they don't want nuclear. So I'm going to scream. I mean, look what Germany did. They shut down their nuclear plants. They're the largest coal-burning nation today, on the top 5.
Really? I didn't know that. Because I knew they were clean energy for a long time.
U.S. is the largest exporter of coal because we've reduced our use. We're exporting coal to Germany.
Yeah, that's
crazy. It makes no sense. Things sometimes don't make no sense, but that's what happens when politics get involved.
Where does this go from here? Because I know, we had some conversation about, like, the potential for some of the other things you could do with this. But I mean, like, what are some of the other ways you can utilize this technology?
So our initial, target market, which is going to keep us plenty busy, both in the United States and overseas, is to be able to extract more natural gas and energy in an economically and an environmental sustainable way. And I think that's going to be our bread and butter. We are eyeing the application of sequestration. So once all these carbon capture technologies or applications mature up, we have to do something with the carbon. Now, personally speaking, I rather do something with the carbon and use it properly if we can. But it looks like there's limited uses, or technologies are not there yet. So one thought process is we're going to put it underground, hence sequestration. So, and there are limits and technical challenges associated with that as well. But regardless, we see ourselves positioned really well. So when that trend does start and the applications start, we could definitely, with our compressors, run them in reverse and able to pack a lot more carbons, existing a space, if you will, downhole, than with any other method. Whatever they're able to do with any other method, we could do twice as much storage. So, that saves significant on the economical scalability, infrastructure, and so on and so forth they need to put in place.
You said something earlier too that I kind of let slip, but I caught my attention. The temperature down there, you said it was over 110 degrees?
The typical temperatures are in Fahrenheit, somewhere around 200 to 240 degrees. Typically.
200. So, I mean, you're above boiling. So you're talking about 104 Celsius, more than Fahrenheit. That's got to make some interesting and unique challenges as well, because, when you heat, like to pump stuff down there, it's going to expand as it heats and things like that.
Exactly.
That's got to be an interesting challenge.
On the top level, like I always say, we could all agree. But as you get down to how we're going to do this and the details and these little challenges, all of a sudden, we're like, somebody will solve it. Well, some of them are, the boundary of what physically possible or limitations that we're just going to have to live with. Right? I mean, it's so much we could do.
Just going back to the pump you've designed and some of the weird challenges you have to face, like operating a pump at that temperature, my stuff shuts down pretty quickly when I get close to, that kind of temperature. I mean, that's got to be an interesting challenge as well.
No one spent 9 years and $80 million on your pump. That's the difference. Yeah.
That's true. I mean, I need one of your pumps, although 12 feet tall might be a little bit much.
No, it does create its unique challenges, absolutely. But you know what? I always believed in innovation. I always believed in technology. When there are issues, technology innovation will solve them. The question is to make it sustainable. It needs to be profitable for it to be sustaining. You can do everything for one-off, government grants, this and that. But in order for something to be sustainable, it needs to be profitable. And that's something that we focused on from day one.
I mean, it seems like if you're eliminating all these compressors, you're getting more efficiency out of the wells. So you don't have to, I mean, I got to imagine starting up a well is wildly expensive. You're probably taking a lot of the costs out of this, right?
Yeah, like I mentioned, forget about the emission and the amount of water you need and so on and so forth. Just pure cash of $10 million you need to drill, frack, put in the pipe, put in the topside infrastructure for this new well to come online. That's real cash.
I'd be curious to see your ROI studies and things like that, because that's got to be really an interesting look.
With the operator, with our business model, it's 2 to 3 months for the operator.
Really?
Yeah. We're not selling equipment. We are really, we're owning our own equipment, and we're being responsible for our equipment. We're the sole point of contact for the client. We are doing the job that needs to be done, which is produce what has been unproducible up to date. If anything breaks down, it's on our nickel. So we remove both capital and human resources from the equation from the operator side. That's why the paybacks are amazing. That's why we want this to spread like wildfires, and it makes environmentally so much sense.
Yeah, well, be careful about talking about wildfires, because
I know. We're just thinking about that when you said it's a horrible analogy. I take that back.
But yeah, no, it'd be selling like hotcakes.
There you go.
Not that anybody knows what hotcakes are anymore, but
not anymore.
So if they want to get in on this, where should they go to find you guys and get in touch with you?
We're now located in Southern California. We have offices in Houston. We looks like we're going to be opening up satellite offices in the regions where our clients are. So it's Upwing Energy. So we are going to start. This is one of those things, we're not going to be putting a lot of marketing behind it, because each of these operators, they have 200 to 300 wells. Once we've demonstrated in their asset that what we're able to do and how easy it is for the operator, it's a no-brainer to give us, 5 wells, 10 wells, and 100 wells. That's how it moves. So we think within end of 2024, you're going to see it in a lot of the assets as fast as we could probably produce and deploy.
And they can find you online at upwingenergy.com.
Absolutely, yes. Upwingenergy.com is where we're at.
I'll put it in the show notes, and we'll hopefully people will get in touch with you and explore this.
Yeah, we'd love to talk to the operators, explain them how it works, show them the demonstrations. I mean, our facilities are always open. We always got something funky going on and operating. We even drilled our own well in here just to be able to mimic and correlate our models with what's going on. So yeah, it's fun.
Tap anything?
No, we were really afraid that we were going to tap into some power lines and water lines, but thank God that wasn't the case.
Yeah, well, what's that? Call Julie before you drill or whatever. My wife's name is Julie too, so I got I got to call you before I dig a hole in the backyard. So
I think she wants you to call her before you do anything.
Yeah, she definitely wants me to call her before I start digging holes in the backyard. What crazy idea have you got now? Well, that's awesome. I mean, like I said at the beginning, I think it's like sometimes everybody wants to solve the climate problem and eliminate all CO2 emissions, but I think one of the things that you point out is that fossil fuels are used for a lot of things, from food production to clothing to, plastics and, all sorts of other things. And so it's not a simple thing to just get rid of. And in making these kind of more significant, but, incremental, but significant improvements in the way that we're producing this stuff can really buy us time, as we're going forward. And I think it's stuff that's really important. And shouldn't be discounted.
Look, I always say, this is a very complex problem, right?
Yeah.
Everybody who thinks that we're going to be able to solve our energy issues with one or two technologies or whatnot, there is no silver bullet in this thing. That we're going to need a mix and blend of everything. And for those who are really bought into the camp that, oh my God, this XYZ is going to take care of all my problems, it's a wishful thinking. All we're doing is pushing the problem further down the road. So it's complex. It's going to take every little bit of everything to make this work. And a lot of innovation along the way. Yeah.
Complex problems are hard to solve and it takes work. And, thank you for doing the work to solve some of these problems. Appreciate it.
Thank you so much for being on.
Thank you so much for joining today. I love talking about this stuff, and we could go on and talk about all the weird nuances of what it's like 2 miles underground and things like
Chris,
that.
You make it fun, and you touch the right questions, and you're able to put me on the spot a couple of times. So appreciate that.
Oh, thanks. Well, hopefully not too bad on the spot, but thanks so much for being on. Really appreciate it. If you want to find out more, go to upwingenergy.com and check it out.
Absolutely. Thank you.
Thank you. Thanks for watching. I'd love to hear from you in the comments. And if you could, please give us a like, think about subscribing, and I will see you in the next one.